So this is Intro to Practical Machine Learning. My name is Shrivu Shankar. I'm an undergrad student at UC Boston. So general overview for this presentation, really going to be more of a machine learning overview than sort of a DIY tutorial. I kind of chose that format because Google, there are tons of blog posts and tutorials that will allow you to do very specific things, but not very good overviews of like general machine learning, which I think is a lot more important. So I'll go over kind of an introduction of the topic, different methods of learning, then actual different models you can use, and then applications. So this is a really common diagram to kind of explain kind of the scope of machine learning and AI. So the biggest circle is just all of AI, kind of the general hype term. Many startups kind of will say AI, but really it kind of incorporates quite a bit of stuff. So it includes kind of like if statements, and then if you get more in depth, if you do things like logistic regression, it would be considered machine learning because you're now learning how to make different decisions. And then it goes even more in depth with something called representation learning, which isn't as common of a term you'll hear. And then deep learning, which is also a major hype, which is at the very center. It's a very specific kind of AI, which is also a specific kind of machine learning. Here's a really common phrase used to describe machine learning. A computer program is said to learn from experience E with respect to some test T, performance measured P, if its performance at test T as measured by P improves with experience E. The general idea of this is machine learning is simply when a computer program is able to do its task over and over again, and its skill in whatever experience E is, increases, and you measure it with some objective. Yeah, this is a really common phrase you'll hear to describe what machine learning is. General motivations, you can have like Netflix video recommendations, self-driving cars, chatbots, kind of Amazon Alexa information retrieval kind of stuff. Medical imaging, this is actually something that's really, really popular right now. Basically, you're able to take x-rays for like MRIs and then detect things on it. And also just kind of like security surveillance, I don't know, in case you're running some sort of deep state kind of thing, you can use AI for that as well. So a big important topic of machine learning is the math. You'll hear this a lot. And it's also a really common question, what kind of math do you know? These are kind of my top 5 sort of regions of math that will come up in machine learning. Linear algebra, probability, vector calculus, optimization, and information theory. And then some scary equations on the right side. I would say in general, linear algebra is probably the most important with probability a close second. You actually see that you can actually do quite a bit without actually even understanding these equations on the right. And so that's why this is kind of like a practical machine learning workshop, because you can really get quite a bit done without actually knowing a lot of the math behind this. But if you are interested in the math, I definitely recommend kind of brushing up on these topics. This is another thing you might see, like boot camps will say, you know, pay for our 6 weeks course and you're basically an AI expert. And the PhDs may say, oh, well, you need advanced mathematical background to do different things in machine learning. I would say both of these could be misleading, but I mean, definitely the PhDs have a point. A lot of machine learning does rely on a lot of fundamental topics. And so I do recommend one of these books, this book in particular, Mathematics for Machine Learning, which kind of goes over different stuff. But like I said earlier, you don't really need that much of a mathematical background to do things. It's still really important in terms of being able to debug things and maybe even like contribute to research and stuff. But if you're just building applications, a lot of this math actually isn't necessary. And you'll see later in the code samples, you don't actually need to really ever like write these equations. So the code is already written for you. So this is going into learning. So if you already have sort of ideas for a machine learning project, you can almost like follow along like a checklist in this section. But basically, this is how different models, I guess the different classes of models that you can have. Before that, I'll refer to a data set a lot in this presentation. So when I say data set, I literally mean sort of a piece of data. And in this case, this is like showing a CSV file that you might have imported. And then once you have kind of like this raw data, you might do things like remove columns that aren't important. So in this case, this is like predicting whether someone survived on the Titanic, and they have passenger IDs. In this case, the passenger ID is a random number, so you can completely discard it because it's not important for the classification. It's not going to be something that you do when you create your data set and going from data to data set. And yeah, you might convert categorical features to numerical values, and this process is generally called feature engineering. So then this is one of the major classifications for different machine learning algorithms. This is called supervised learning. And the general idea is you have X and Y, and you're finding a model that predicts Y given X. And then this can be broken down into two different classes. Classification, this is if your model is predicting like a yes or no answer, or maybe several classes of answers. And usually like if you have like discrete labels, this is something cool. Then you have regression. This is where you're trying to predict sort of a continuous value. So you might think of this as like predicting price of a house or a stock price or the age of someone. And most of the time you can actually do something called binning, where basically you take, you might, if you have a number between 0 and 10, you might make all the numbers between 0 and 1, one value, all the numbers between 1 and 2, a different value. And basically you can turn it into a classification task, which is really common. And then I have two examples here. For classification, hot dog, not a hot dog is a common one from Silicon Valley. Basically you might have a ton of pictures of either hot dogs and not hot dogs, and then you can basically train a model based on that X and Y data to do that classification. And this is kind of another thing about supervised learning. This is something that happens a lot for beginners. They might run their model and they see they have really high accuracy, and we'll go over kind of accuracy later. But generally it performs way better than expected. In general, when it does this, it's actually bad. I say it's okay not to be perfect. You usually, if you're looking at 98 or even 80% in some cases, might be really way better than having 100%, because it usually means you're doing something called overfitting. Overfitting is kind of equivalent to model memorization. A good analogy to this might be memorizing previous tests versus studying. Someone might literally just look, if there are 5 previous tests and they know the next test is going to be just like the other ones, they might just memorize those answers. But then if the test is completely new and rewritten, then they basically, they fail the test, versus if they studied. The mathematical equivalent of this is kind of shown in the picture on the right. Basically, you have red and blue dots, and then kind of a black line between them. The black line is what you want, but what overfitting might do is produce that green line, to where it kind of decides to be a little bit more complex, and that complexity kind of causes this memorization, which might actually lead to better than ideal kind of results. And then an easy fix for this is simply just getting more data. And then along with that, a common thing that's going to be done is you'll split your data set. So like looking back at like that CSV file, you might say the first 60% is training data, this next 20% is your what you call dev set, and the last 20% is what you call a test set. The train is for training, and you'll see code for training later. Dev is for tuning, for hyperparameters, which I'll also have in a later slide, and then test for testing. If you're training using some popular frameworks, you'll see usually that your error over time kind of looks like the graph on the right. It will take sort of a U shape, and that's basically showing you how you're overfitting. Past that little yellow exclamation point, that means that you're starting to memorize. And then before that, that means you're actually learning. So most of the time you'll want to stop training whenever you get to that point. So another type of machine learning, if you only have one type of data, is called unsupervised learning. And this has sort of 2 main kind of use cases, and there's a ton of like sub cases. The main one's clustering. This is good for if you want to do like anomaly detection, group detection. You might have a bunch of data in some high dimensional space, kind of like shown in this diagram, and then you want to say like, can I kind of group these in different ways? Usually you don't actually know what these groups are ahead of time. So that's why this is unsupervised, meaning non-labeled. Then you have dimensionality reduction. This is incredibly useful for if you have a high dimensional data set, maybe with tons and tons of columns, and you want to reduce it to something that you can kind of visualize in two-dimensional space. Then you can do something called dimensionality reduction, which can basically produce things like this image here. Basically, they took a bunch of images and they reduced it into 2D space. And basically, images that are closer to each other in the space are close to each other in the actual like higher dimensional space. So it's a really handy technique. And then other uses of unsupervised learning might be denoising. If you have a ton of images that maybe have like watermarks or something, you could train a model that could remove those kinds of things. Or embeddings. Basically, embeddings are representing kind of more abstract topics as vectors. So you might think here, you're representing words with vectors. So drinking, drank, swimming, and swam. Embedding is the process of taking those words and then creating a vector that sort of represents its meaning. And then probably one of the most difficult ones and one of the newest ones as well is reinforcement learning. This is where you essentially place the model in kind of a wild environment, and then you just kind of let it figure stuff out. I mean, there's no necessarily like X or Y. It's really just the model itself in an environment. And then you reward it, and then it learns based off of that reward. So a common way you'll hear this described is basically an agent observes the environment, takes an action, and receives a reward, and then it repeats. And this diagram on the top right kind of shows general process. And that's really common terminology in reinforcement learning. This is also combined often with other methods. At some point, you might say the reward function is based off of classification. So you might then combine reinforcement learning with supervised learning. And this is also commonly researched used in video game environments. Because most of the time you can't afford to run these in like an actual time scale, because like this kind of cycle might take like a day or a minute or something in real life. But if you simulate it using like a video game, you can do it thousands and thousands of times per second across multiple machines. So you actually really commonly see these models that are for real life applications tested in like fake worlds. And then reinforcement learning was used for DeepMind, AlphaGo, and OpenAI's Dota bots, if you've heard of those. So this is transfer learning. Basically, this is kind of a subset of those groups. A lot of times you might not have enough data and you want to use someone else's model. And a lot of times, like you might train like a classifier, for instance, and that might take like a week depending on how big the model is. And a week is a very long time to train. So you can basically take a model that was trained on something that was more complex and use it to solve something that's simpler. So if you ever find yourself, I guess, not having time to train or training is taking too long, I would definitely look into how you can use transfer learning. Here the example is ImageNet on the left. Basically, it can classify all these different images. And then you're able to reuse that model to then do like something like cat versus dog, which even though the original model wasn't trained for that, it was trained on something more complex. You can actually use it like that. Cool. Methods. So these are going to be the models. Decision trees. These are basically if statements, but the model is able to come up with them. Basic example is shown on the right. Basically, for each part of your data, it's able to come up with a way to divide the data into another decision, and then combine that into another decision, and so on. And at the end of the decision tree, the leaves are basically the classes. Pros of this, it's interpretable. It's very easy to look at this diagram on the right and say, how is it making these decisions? Not much, you can basically use your data raw. You don't have to do as much feature engineering as you might need in other applications. And it's pretty robust with missing values. Cons, overfitting, underfitting. So it can either memorize too much or it might not even be able to handle problems at all. Like it might not be complex enough versus being too complex. And it's not super great for some regression tests. Some keywords you might hear for decision trees is ID3, which is a type of decision tree, or random forest, which is kind of a collection of decision trees that are used. And then for each of these slides, you'll see like little code in the bottom right. And that's basically how you would actually use this in an actual like coding scenario. And you'll see a lot of these, it's like super simple using Scikit-Learn. It's like 3 or 5 lines. Another really common type of model is support vector machines. The general idea is kind of like linear regression, but linear regression with bounds. So if you see in the diagram on the right, it's basically drawing a decision boundary in red, and then it has a little gap. And the gap allows it to sort of to confidence estimation and a lot of other fancy probability stuff behind the scenes. But yeah, in general, it's basically sort of like a linear regression sort of thing. And it works very well with complex features, and it has something called kernels. So in the case that your data, you can't literally draw a line through it, you can actually morph the data in a way that you can draw a line through it. And that morph is called a kernel. Some common issues is overfitting, and it can be pretty inefficient for some very large data sets. Keywords, SVM, linear SVC, and then RBF kernel. RBF is just a really common type of kernel that you use. Another common machine learning model is nearest neighbors. Basically, I mean, it's kind of self-explanatory. You're looking at the points that are near the test point. And you're basically saying, what classes do those points have? So on the diagram on the right, the green point, you're trying to figure out what it is, and you say the closest 3 points are blue, blue, and orange. And so you basically arbitrarily say, then it must be blue. It's very sort of a naive classification kind of thing, but it's simple, easy, and it can be pretty fast, as long as you don't have way too many features. And it's commonly abbreviated KNN. Then there's naive Bayes. This is basically one of the very statistically backed models. I mean, they're all statistically backed, but this one is directly based off of something called Bayes theorem, which you probably see if you take in intro stats. And that's basically, I mean, it applies the formula and outputs the result. It's fast, statistically backed, and it can work really well with high dimensional features. Cons, it's called naive Bayes for a reason. I won't go too much into this behind it, but it makes a couple of assumptions that will absolutely break for certain use cases. And so most of the time, I actually don't see this used that much. It's usually tested, but then not used. Common keywords for this might be Gaussian, MB, and multinomial MB. Those are basically different methods of doing naive Bayes for different kinds of data. Neural networks, I crammed a ton into the slide. But basically, this is a general summary of what they are and how they're used. The general idea of neural networks came sort of from like a neural inspiration, you know, like neurons. But I would say it's pretty limited, and the connection is often pretty overhyped. But yeah, they're sort of like neurons, but then they're not very like biologically inspired. So I guess that's my hot take on it. General idea is kind of the perceptron in the top right. You have several inputs, you sum them up, and then you apply a function, and you have an output. It's a very simple idea. And then the general idea of a neural network is you connect those up in the other picture shown on the right, and you're actually able to learn a very complex function by connecting them up. The pros of this is it can have very fast prediction times, and it's very flexible and customizable. How you wire these little units of perceptrons up is very arbitrary, and there's so many different ways you can connect them, and often those are called architectures. Cons, it's very, very easy to overfit. If you have too many neurons, you might have a perfect training accuracy, but you might never have a good test accuracy, which is what you want. Training this can be incredibly slow, and the interpretability of this is really bad. I mean, just looking at the picture on the right, it's not easy to determine how the model is actually making those kinds of decisions. Some terminology that is really commonly associated with neural networks is a loss. It's basically how bad the model is in its current state. It's kind of similar to accuracy, but a little bit different. Optimizer is basically how the loss is used to improve the model. You hear things like SGD, Atom, yeah. momentum. Yeah. Then you have learning rate, which is basically how fast you do that optimize. And so usually learning rate and optimizer are used like very closely together. Then you have an activation function, which is basically how the perceptrons use their inputs. So if you look in the perceptron image on the top right, you kind of see there's like a summation symbol and then sort of like the integration symbol. That is basically that activation function. You apply something to the sum of the inputs. By varying that, you can kind of vary how the neural network's working. And then common references to neural networks, NNs, ANNs for artificial neural networks, and the multi-layer perceptron. So with neural networks, by making very large neural networks, you do something called deep learning. And there's probably the most hype around this in general for machine learning, just because it's able to solve very complex models that previously couldn't be solved by some of the other methods, which is pretty incredible. General idea is you literally just kind of chain neural networks to be very, very deep, kind of like the picture on the right. And then by becoming deeper, you're able to create a more complex function. Cons, it's very easy to overfit because you're making it more complex. And so it's easier for it to memorize, and the memorization is bad. And then super long training times. And you might even need like GPU hardware to do this kind of computation. And then these come in a ton of different shapes referred to as architectures. Commonly abbreviated DL, you also see something called CNNs, which is a type of deep learning model. That's primarily for images. And then RNNs, another kind of RNN that you might hear about is an LSTM. And those are primarily deep learning models geared towards text or sequences, or if you have like time series data. And at the bottom here, I included a picture of InceptionNet. That is a very popular computer vision type of CNN, convolutional neural network, that's used for like photo classification. It's even been used for like self-driving cars and stuff. And you can see how weird looking it is, and that's kind of sort of a testament to how kind of customizable these networks are. So some meta kind of stuff about these kinds of models. You often hear something called hyperparameters. And this is really sort of the things that can't be trained in general. So like how many layers do you want to put in the machine learning model? What is your learning rate? What is your batch size? How big should you make the random forest? These are all hyperparameters. And you basically, for your model, you want to find whatever the best hyperparameters are. Some common methods for finding that are grid search, random search, and Bayesian optimization. Grid search is basically what's kind of shown on the right here. It's the equivalent of kind of having a for loop for every different parameter, and then you basically just try everything, kind of a brute force kind of thing. And then random search is basically you just kind of use math.random over and over again, and you just use the best model. It turns out that random search actually works significantly better than grid, or grid search. And so that's often what's most used. But sometimes there's an additional optimization on random search where you use sort of Bayesian statistics to improve how you're randomly searching the space. It's key to remember that, so you're training on the training set, you're tuning on the dev set, but you're not tuning on the test set. So when you do this kind of figuring out what hyperparameters is best, you should not use your test set, because you actually can, in a way, have your model memorize the data by randomly, or by trying all the different possible values for hyperparameters. That might be confusing, but general idea: training set for training, dev set for hyperparameter tuning, and then test set, you only run it once or twice to see how well your model's doing. Another thing about these models is metrics. So I mean, there's so many different ways you can evaluate whether your model is good. Very common ones are accuracy, where it might be literally what percent of sort of training examples were labeled correctly. Another really common one is just mean squared error. So I mean, that's literally, you find the difference and then you square it. Also called L2 in a lot of things. Sort of branches off of that, precision, recall, F1 score, which is based off of precision and recall, area under the curve, mean absolute error, and there are actually quite a bit of these. But I'd say for the most part, you can get away with using accuracy and mean squared error, and only if you have maybe an unbalanced data set, or you have different consequences for like false positives and false negatives, then you might want to use a different kind of accuracy metric. So this is applications. So kind of going through kind of what I talked about in the previous slides, if you have sort of this problem where you have a bunch of pictures of digits, and then you want to classify them 0 through 9, you can basically, or I guess the way you use the previous slides or the information on them is you take the image and then decide it's a supervised classification problem. So you have X and Y data, meaning the images and then the numbers. And you might choose a neural network. You might decide that the number of layers, the number of units in each layer is a hyperparameter. And then you might say that your goal metric is accuracy. And that's pretty much it. I mean, you can basically go from like the raw data, choose what kind of method you want to use, and then basically use like Scikit-Learn or Keras or something to build the model. And here's basically an example of what that looks like. So hopefully you're able to see sort of how like the left side translates into the right side. But yeah, the hard part is really coming up with kind of what kind of model you want to use and like what's learning type and hyperparameters. Cool. A lot of this can actually be done by APIs. So I'd recommend if you're not that into doing it yourself, there are a ton of applications that can actually do a lot of this for you. And might even try all the different model types at the same time. So you don't actually even have to worry about the different kinds of models or even like train, test, dev kind of stuff. So I highly recommend kind of things like Google Cloud and AWS machine learning APIs. BigML is also good, Wood AI. And there's also something called AutoML, which basically will literally do everything for you. You throw in the data, it does whatever magic behind the scenes, and it pops out a model that allows you to predict. This is incredibly cool, and it's like powered by the machine learning experts at Google. Then the price is like incredibly high. You might be paying like something like $15 per hour in some cases for AutoML. But a lot of these other ones are free. If you do want to do it yourself, these are kind of like my top 4 libraries for machine learning. And I definitely recommend if you want to use one of these, just Google like the quick start guide or a tutorial. So Scikit-Learn, that's basically for all things machine learning, data science. TensorFlow, specifically geared for deep learning. Keras is sort of a part of TensorFlow now, but it's sort of like the Legos deep learning kind of thing. It's very easy to basically just add layers, kind of just stack things. I definitely recommend Keras if you want to get into deep learning. And then PyTorch, that's sort of the rival to TensorFlow, and it's created by Facebook. But both TensorFlow and PyTorch are considered like the hardcore ones, I guess. But I definitely recommend if you really want to get into this to learn at least one of those. These are some helpers. I would say you probably need to know all 3 of these. But I guess that's my personal opinion. Definitely Python. I would say Python, C++, and R are like the main ones used in machine learning, but more and more Python is like the most common one. And then along with that, pandas and NumPy. Those are some really common libraries that are used. So some applications of machine learning and computer vision. I have a bunch of tasks here. Going left to right, object detection. You're basically finding objects on the screen, classifying them. Image generation, you're basically able to synthesize different kinds of images. Here it's like messing with faces. Pose estimation, you're able to take an image and then compute their pose. Style transfer, you are basically able to take the style of one image and then an actual image and then combine those and make some really artistic kind of things. And then Super resolution, this is literally like enhanced for movies. You're able to use machine learning to predict the interpolated pixel values and actually increase the resolution of a photo. And then classification, basically you're taking a picture and you're classifying it. So these are all computer vision, machine learning tasks. If you see these that you're interested in, I definitely recommend either asking me later or kind of just Googling the topic and say like, how do you do this in Keras? And you'll probably find a tutorial. This is natural language processing. This is machine learning and language. So some common tasks here are machine translation. Google Translate itself is powered by machine learning. It's really cool. They actually released a lot of their research, and so you can actually see some of the models that are behind this. Question answering. This might be also kind of like a Google search. You might ask a question that's written in human language, and it's able to translate that into a query that can then be used to actually like analyze and search data and then return a value. Sentiment classification, that's pretty self-explanatory. You basically have like a statement or document or even a word, and then you're able to say, is it like negative sentiment or positive sentiment? You have text generation. If you've seen something called GPT-2 recently with OpenAI, that was a pretty big thing. Basically, you're able to generate fairly realistic text now in 2020 that can actually fool humans, which is pretty cool. So yeah, NLP for text generation is pretty popular and really advancing. Image captioning. This is where the AI is able to take an image and then literally come up with like a sentence that describes the image. And then you have classification where it might read emails and then decide if it's spam or not spam. And then I guess popular starter data sets. And in case you're interested, I definitely recommend looking at MNIST, which is the digits one. And then the large movie review data set, which is kind of NLP. You're basically doing sentiment analysis on movie reviews. And then Kaggle is another source. Basically, Kaggle is sort of like this competition website, but you don't actually necessarily have to compete, where they have tons and tons of data sets. And basically, they have some sort of objective. And you can like try out your machine learning skills there. And I definitely recommend starting there. Cool. That is it. Are there any questions?
Hey, yeah, I had a question.
Sure.
I was wondering, like, if I wanted to, like, you covered a lot of topics, so it's really good, really interesting. If I wanted to like go deeper and like, I feel like I have a math background, but I don't have a lot of knowledge on these topics. What would be a good way to like start getting a good background?
So you say you have a math background, so I guess you're looking for like a computer science or programming thing, right?
Oh no, I mean, I guess like I can do math and programming, but not like specifically like machine learning. Like I don't know much about like how to like I don't know much about these topics, but I guess I know like linear algebra, probability, and programming. But
Gotcha. Yeah, I mean, I would say like if you have machine learning and programming, then like Scikit-learn is probably something that you want to look at. Yeah, I mean, basically just look for code samples, look for this kind of models mentioned earlier. And yeah, I think the docs there are really good.
thanks.
Cool. Any other questions?
I have like a general question that might help some of the teams. So like we are hosting like a hackathon, right? And like a lot of hackathon projects, you don't need to go that in depth into like the ML like sphere, I guess, and you just need to know like the basics and like stuff. So like where would you suggest teams start if they're like, oh, I know like I kind of want to use ML for this, but like I don't know what kind of model and like what kind of like which tool to use. Like what would you suggest teams that are in that boat kind of do?
Sure. Yeah, I would say probably the easiest way if you're in like a hackathon kind of situation is just to use pre-existing APIs. So definitely look at like the machine learning API for Google, and then also like Amazon, with AI and BigML. Those are all really easy to like quick start, and those will basically give you I guess the bare minimum to start doing AI, and then you can kind of go from there. Someone had one in the chat. Okay, how do I know which model to use for my particular problem? Honestly, easiest way to kind of easily distinguish at the beginning is to look sort of at the pros and cons, know your problem. And then the next step would be, of all the models that work for that problem, basically try all of them. In most cases, you might actually be surprised that one model works better, even though intuitively it might not. But usually there's not like a very definitive, always right answer for finding which model is best. So generally, especially Scikit-Learn makes it easy. Just try everything that makes sense. Yeah, so do the AWS, et cetera, credits provided by the organization cover the cloud APIs? Yeah, so both AWS and machine learning, I believe, or Google APIs cover, give you like $100 or $300 for the credit, and that will work for all those kind of machine learning applications. Honestly, you can go pretty far with that. I think it's like literally in the cents per API request. So yeah, I definitely, these are free for practically, they're free with the amount of credits that you get.
Hey, so let's say I have a trade model that I acquired from one of the tools you mentioned. What's the easiest way to get it up and running on, let's say, a server on which I want to have these models running?
Sure, yeah. So let's just say you built a model in Scikit-Learn. Probably, I mean, these don't usually require, I mean, in terms of like a hackathon scheme, not like a production environment kind of thing. You can basically just load the model as like a pickle file or an H5 file, and then just call predict in whatever web server endpoint you're using. Usually the predict like function maybe takes probably less than a second, so it doesn't really block or like time out the request. So yeah, I would say it's generally not as bad as you might think to just literally invoke the model in your like endpoints on a web server, for instance. Yeah, so I'd just say just calling it usually works. And I recommend Flask for people who aren't familiar with like web servers and stuff. It's very easy and straightforward. You can even look at Scikit-Learn in Flask or Kernels in Flask, and there's a lot of resources.
And if you need help with Flask, you can check out my workshop from yesterday, available on YouTube. Are there any last questions? Oh yes, Misha would like to ask you, what is Google Colab?
Yeah, Misha heavily sponsors Google Colab. Basically, there's this really handy thing. So installing these can be fairly difficult. I would say maybe not Scikit-Learn, but Keras, TensorFlow, and PyTorch can have issues because a lot of times they like hook on to hardware level stuff in your computer. So Google Colab is basically a online resource that you can use, and it's like a Jupyter notebook. You've used that before. And basically, it's just a place to write code, like a little text editor / notebook thing that has everything set up for you. So a lot of the hassle you might find, especially if you're kind of new to programming in Python or in general, is literally just installing things. It's a pain. So Google Colab is a good way to skip all those kinds of difficulties. Another recommendation, there's actually a ton. I actually don't remember it off the top of my head, but there's actually a bunch of Google Colab like things. But Google Colab is one of the free ones. So yeah.
A good analogy is like Google Colab is like Google Docs to Google Drive is like Jupyter Notebook to Google Colab.
Yeah, yeah.
It's like the Google Drive for your code. It's lit.
Cool, yeah.
We have a question in the chat.
Yeah. For those trying to learn TensorFlow, PyTorch APIs, do you have any particular resources that are helpful or good projects to start with? So I would honestly just like Google for the documentation on it. I think everything on this PowerPoint was mainly sort of getting you acquainted with the terminology and the different kinds of models. But in terms of using these like 4 things for your thing, I definitely recommend literally just Googling like quick start or how to use this model. And the docs are really great in terms of getting started. So I would just say try the official docs. And are there good projects to start with them? I would say like kind of the projects mentioned here. I would say these are 2 fairly simple projects that are really good at sort of doing the full pipeline of going from your data set to like a final output. MNES is usually considered like the hello world of machine learning. So I definitely recommend that. And you'll see tons of resources. If you say MNES, Scikitlearn or something, there'll be probably thousands of implementations that you can look at if you get stuck. So.
Alrighty, I think that is about all of the time that we have. Thank you, Shrivu, very much for presenting. Thank you, everyone, for coming. If you have any more questions, feel free to direct them to our Help ML channel or straight to one of the organizers. We will be happy to answer them or forward them along to Shrivu for you. But anyway, thank you, everybody, for being here. Have a great rest of your day, and we hope to see you at our workshop tomorrow.
Cool. See you guys.
Thanks,
Thank
Shrivu.
you, Shrivu.
Appreciate it.
That was awesome.